I'll just be back in a minute.
Yeah.
Okay, okay.
I will start in a minute. Yeah, you can come back.
Okay, thank you. Hello. Yeah, I'm back.
Okay. I think you are the only one participating today. But I'll post the
Oh, I
video.
think there is someone else as well.
Is it?
I just saw 4 participants.
Okay, hold on. Let me see. Oh yes. Okay. Cool. Okay, so let me get started. So recall. So I mean, just I'm going to do a quick recall, and then we'll take from there. So so rho has a spectral decomposition. So generally we write rho as let's say lambda I I equal to 1 to d. So what we are doing is we are just writing this the same thing as I will just say X is the set 1 to d, and I instead of lambda I, I'm going to call it Px of X Ex. So there's no big difference really, just the notation, but the notation helps us with the definition we had for typicality in the classical case. Okay, so so T delta n of rho is defined as the span of the following subspace. So you take all these vectors cx1 exn such that x1 through xn, which can be denoted as xn, belongs to the typical set. When I look at px, this is the classical definition of typicality. So you have to just see the number of indices must be similar to the proportion of the indices must be close to lambda i's, the proportion of the lambda i's or the px's. So that is that, and we define the typical projector by rho delta n to be the following. Essentially, I'm projecting on this above subspace. So this is going to be the rank one, the summation of the rank one projectors corresponding to each of these. Okay, so if you have any questions at any point, just ask. Exn Just with me also. So hold on, give me 1 second. One second, I'll just so that I can. Okay. Okay. So okay. So okay. So this is the typical projector. And so there are three important lemmas, very important lemmas. So the first, I think I will copy paste. I did not write it formally, right? So I will write it down formally. I think I just mentioned it if I'm right. Yeah. Okay. So proposition. So three important results. Given any row and delta greater than 0, there exists an index sufficiently large. I mean, there exists an index such that for all n greater than equal to n delta rho, you have the trace of the overlap between the typical subspace and the quantum state is very large. That's really all it says. 1 minus exp. This term is going to be n. Okay, so what I'll do is I'll just, just to be not, there exists an n, and I will just say, give me 1 second, and an alpha that depends on delta rho and delta, which is greater than 0. So there is a positive exponent at which this quantity falls. Okay, I'll just write this. So this alpha delta rho delta will be that you have that cardinality of x and all that comes into picture. Delta. This is what you get. Okay. So you can pull this alpha delta. You can pull this from your previous expression. This is going to be from your Hubding bound. Okay. So this is the proposition. Anything else? Okay. Okay. So I will say this is 1. Okay, and 2. The dimension of this subspace. See, your rho tensor n actually lives in a dimension of space d power n, right? So, so I will state that at the end of the day. So, if I look at the dimension of t rho delta n, which is also equal to the trace of the projector, right? If I take a subspace and I look at the dimension of that subspace, it is the same as the trace of the projector. So pi rho delta n, these are tightly, their exponent, the exponent is tightly coupled, so is very close. So what do you get? You get 2 power. I'm instead of writing 2 power, I'll write exp. Okay, exp n times s of rho plus delta. And at the bottom, you will have this 1 minus e power minus exp. So it's almost 1, but there is this correction factor, I mean, a small correction factor, which is actually just, squishing itself to 1, essentially. So this thing times, so I need a little bit more space. Exp n times s of rho minus delta. Okay, so you have this, and third one.
Sorry, just one question. Sorry.
Yeah, please.
So this dimension of T delta n rho, that will just be the size of T delta n, right? T delta n. I mean, it will end up being that.
T delta n px. Yeah, that is true. It will just be end up being the size of T delta n px. That's true. Because see, okay, I'll tell you why. Because observe that if I take xn and x tilde n, two different sequences in xn, observe that e x1 tilde all the way until e x tilde n, inner product with ex1 exn, observe that this is 0, or it's in fact it's equal to delta of x tilde n xn. You agree?
Yes, yes.
Yeah. So hence you're essentially just counting. So you're essentially just counting the number of terms inside this. That's exactly what this is. Because of spectral decomposition, the entropy of px is the same as the von Neumann entropy of rho. You agree?
Yeah.
Okay, great. And the last one, this is the most important, I mean, not the most important, but this is an operator inequality. Remember, in the classical case, we say for every xn belonging to t delta n px, the probability of that sequence with respect to that distribution px is within 2 power minus n times h of px, right? You did this in the homework. Instead of saying for all, now I have an operator inequality. Okay. So when I look at this, so remember pi rho, the other thing you should keep in mind is pi rho commutes with rho tensor n. Okay, it's a very important point. Pi rho delta n, this is a very important, two operators commuting is a very strong thing. So these actually commute because, so I'll show you that, I'll maybe mention that. So this thing is upper bounded by exp minus n times. Okay, each eigenvalue is upper bounded. So that's the point here. S of rho minus delta, because I have a minus sign, pi rho delta n, and on the left hand side I have exp minus n times S of rho plus delta. It's a smaller quantity, pi rho. So this is an operator inequality. So this operator dominates this operator, and this operator dominates this operator. So the eigenvalues are squished. And in particular, I'll just write this. This is just I mean, really, I don't need to say this, but in particular, pi rho delta n and rho tensor n commute. Okay, so I will write this down. Rho tensor n equal to rho tensor n pi rho delta. I mean, this is not really in particular. Also note that, I will just say, also note that. So I've included all the three statements in one go. See what is happening. What is the import of this? See, rho, right? Rho, it lives in this. This is the ambient space, right? And rho tensor n lives in an ambient space of dimension d power n, right? So this is what it is. So rho tensor n. So if I look at the dimension of the ambient space, this is actually d power n, right? But what I'm saying is essentially rho tensor n is localized in a space of dimension 2 power n s of rho, exp n s of rho. Okay, so this is exactly the very similar to saying, you know, when I take px, well, px, suppose I take this distribution, px 0 is 3 by 4 and px 1 is 1 by 4. Yes, this distribution px has a support of size 2, right? And so if I take px, I am used to writing tensor, but let's say px all times px, so this is pxn. This has an ambient space of xn, which is size 2 power n, right? So sorry, this size is 2 power n, but what I'm saying is, okay, in this size set 2 power n, really everything outside this very small set of size 2 power n h of px, really px doesn't live outside this at all. And similarly, now we are thinking of row tensor n. It's a big space in which it lives, right? I mean, well, I shouldn't be writing this. So it's I mean, just for clarity, it's a big space it lives in, but really it's really it is caught up in in a plane, in a lower dimensional thing. I'll just write a line. So it's really stuck in just a, I mean, it's really localized in just one line. And if you take a projector with respect to that line and the projector orthogonal to that plane or to that line, you will always get the measurement corresponding to that line. So that's really what the typicality is saying. So it's kind of localizing it for you. Okay. Okay.
Sorry, this blue line that you are taking to be T delta N, right? This blue line.
Correct. Correct.
Okay.
Instead of write, I'm not able to write a plane nicely, so I'll just write a line. So it's a lower dimensional subspace. And this is, yes, this is your T rho delta N. And in some sense, this is your H tensor N. Okay. Okay, cool. Now we will go, I will introduce one more thing similar to, so now I have kind of done the analog of classical unconditional typicality, in quotes unconditional. Now I'll do conditional typicality, and then I go into packing lemma. I'll motivate the packing lemma, and it's very interesting. So this conditional typicality is important. So kind of just let's go through it. Let's understand this. So the proof of all this, okay, I'm really going to give this as homework, because it's simply what you do is you simply plug in the classical tip. I'll give you a sketch of proof of the first one, and you will see how much it just completely is just a restatement of the classical typicality. Okay, I'll just give you a sketch of the first one. So recall pi rho delta. What is this pi rho delta? N. This is essentially this, right? Xn belonging to T delta n px. EX1 EXN, rank 1 projector EX1 EXN, right? What is rho tensor n? Rho tensor n is, well, everything, right? Xn belonging to, this is the difference, this is Xn, Px1, sorry, Px of x1 all the way until Px of xn. I'm just writing it, I will call this, let me just do, instead of xn, I don't want to get wrong with the notation, so I'll just use x tilde n instead here. So just to ensure that the I don't get wrong with the dummy variable ex1 tilde n, sorry, this is n, there is no n at the top, ex1 tilde all the way until exn tilde, right? Again, sorry. Okay, so now when I multiply these two, right, what do I get? So I am multiplying this and this, right? Remember again the thing I mentioned in the previous thing. So if xn okay, so let me do this. Pi rho delta n rho tensor n. It must be obvious, but just for completeness, I'm doing this. X tilde n. This xn belongs to T delta n px. This x tilde n belongs to xn, and I am going to multiply these two objects, right? These two paste. So I have something like this. So I'm going to pull this to the left, and I have this here, and I have this here, and I have, I'm just going to squish this a little bit and put it here. This is what it is, right? Now look at this. Look at this. This will survive only when xn equal to x tilde n. So you will essentially have the summation to be just one summation, which is going to be xn belonging to t delta n px. The rest of the terms just go off. Px1 of x1 all the way until pxn of p. There's no x1 here, sorry. Xn ex1 all the way until exn, ex1 all the way until exn. Now, when you take the trace of this operator, you will just be summing over the probabilities, and that will be just your typicality probability. So it's just identical. It just completely boils down to the classical case. If I went too fast, or you want another view of the sketch, let me know. I'll explain, but I'll just leave this here like this for 2-3 seconds before I go to the next one. Okay, it's okay with you?
Yeah, it's fine.
Srinidhi? I didn't hear you. Srinidhi, you're there. Okay. Can you please explain the last step? Yeah, sure. Okay. So let me. So this is 1. This is 2. This is 3, and this is 4. I think 1 is by definition, right? That should be okay. 2 is also by definition, because my spectral decomposition of rho is this px of ex1, ex tilde, right? So by spectral decomposition, that is rho. So rho tensor n is this, right? See, I have to compute. What should I compute? I should compute the trace of pi rho delta n rho tensor n. So I will just look at, first I look at the operator, the product operator. That's what I have here. So I just did copy pasting. So so I'm going to write it in gray. So this is your pi rho delta n. This is your rho tensor n. So I just pull the two summations together. Just write the two terms. Only thing is this inner product. Yeah, this inner product comes here. I have pulled the scalars to the left. That's all I've done. I haven't changed the order of the operators. Okay, so this is your pi rho, this is your rho tensor n. So now you have this inner product sitting here, and this inner product I told you is equal to 1 if and only if x1 to xn is identically equal to x1 tilde to xn tilde. That is, each x1 equal to x1 tilde, x2 equal to x2 tilde, all the way until xn equal to xn tilde. So that means that this double summation will essentially become a single summation, with the second argument being exactly equal to the first argument. So whenever x tilde n is not equal to xn, that term is 0. So I have only one term in the summation. The probability is there. So x tilde n, now I'm just renaming it. So xn should be equal to x tilde n, and since xn is summing over the smaller set, I'll just take xn belonging to this. This thing, whenever xn equal to x tilde n, it becomes 1. So I can remove it. So I have this outer product of this and this term, and that's, well, because xn equal to x tilde n, it's the same outer product. So this is what I have. Now I have to compute a trace of this whole object. I have to compute a trace of this whole object. And then when I do the trace, I'm going to get this outer product will become an inner product. That will be 1. And I'll just have a summation. So let me just write the last step. So trace of pi rho delta n rho tensor n is going to be summation xn belonging to t delta n px. So I'm writing the same term here, px of x1 all the way until px of xn times 1, because the trace of this becomes 1. So this, what is this? This is essentially xn belonging to t delta n px. Pxn, so xn. This is exactly what you did. This you showed is greater than 1 minus epsilon times 1 minus exp with the Hopding inequality in your homework. So that's, so I have essentially shown that this guy is dominated by this expression. which is exactly what is there, what I was asked to prove. Is that okay? Okay, cool. Okay, so now, so that is unconditional typicality. Now I'll go to conditional typicality. So essentially what I'm trying to say is that the proofs here, if you just start to write them down, it will be very similar to the classical typicality. That's why I gave that as a homework, so that you're kind of familiar with it. So even this one, right, you're just counting, as they just said, you're just counting the number of typical elements, and that is exactly what it is. And the entropy of px, the Shannon entropy of px, is the von Neumann entropy of rho, because I've done a spectral decomposition, and it's the entropy of the eigenvalues. So that is, so this bound comes just free of cost. The third one, very similar. So I will leave that.
I just have a question about the third thing.
Yeah, please.
So when you talk about operators, A less than B less than C, for example, that just means that B minus C is like less than equal to 0. Oh, so let's just talk about, let's say A is less than B. Let's say you write A less than B.
I'll write the definition.
Yeah.
A comma B, two operators satisfy, or say for two operators A and B, we say B less than equal to A, or A greater than equal to B. I'm just writing because I'm just for mnemonic. If for all x in H, x A minus B, x is greater than equal to 0. And I mean, the remark is that if A minus B is Hermitian, is self-adjoint, then A minus B, A greater than equal to B is then this, if and only if A minus B is positive semi-definite. So all its eigenvalues are, or all the eigenvalues, singular eigenvalues of A minus B is greater than equal to 0.
Okay. So when they are Hermitian, you can think of it like all the eigenvalues of A are more than eigenvalues of B.
No.
Because you said something about eigenvalues. That got me confused. Okay.
No. If it is this way, right? And B is V gamma V. So I'll use the big gamma V. See, all the elements of lambda may be greater than, so lambda I may be greater than gamma I, but A minus B need not be positive. You should look at A minus B, do the spectral decomposition of that QD Q dagger, sorry, this should be daggers. And then if the eigenvalues of D, I are all positive, then you can say A is greater than equal to B. You have to be careful.
Okay.
You see the distinction, right?
Yeah, because when you talked about the point 3, you said that the eigenvalues are squished like that. I got confused there. Like you just
see,
so what?
So wait, let me explain this. So see, when you have two operators A and B, okay, let's say two Hermitian operators. So they're in R of H. Sorry, I mean self-adjoint operators. Now A can have a spectral decomposition, U lambda U dagger. B can have a spectral decomposition, B V gamma V dagger. Okay. Now all the eigenvalues of A may be greater than or strictly greater than the eigenvalues of B. But A minus B need not be positive. So in other words, but A is not necessarily greater than B. The reason is that remember for A minus B, for A greater than equal to B to hold, you need A minus B to have non-negative eigenvalues. Okay, so A minus B should have non-negative eigenvalues. So in this case, what could happen is when you do the spectral decomposition of A minus B, you may get Q D Q dagger, and it could turn out that all the DIs are negative.
Yeah, correct.
So in which case A and B are not going to be, A is not going to dominate B as an operator. Now, in the case we were talking about, that's why I mentioned this. See, okay, so this is this, but suppose I tell you something more. Suppose I say A, B equal to BA, A and B are self-adjoint. Suppose I tell you this, then your statement is true. Sorry. Then your statement is true that if the eigenvalues of A dominate the eigenvalues of B, you know, when I say eigenvalues of A dominate the eigenvalues of B, the corresponding eigenvalue, so the eigenvalue corresponding to a particular eigenvector dominates the corresponding eigenvalue of B with respect to the same eigenvector. If that happens, then I can say that A is greater than or equal to B. Okay. Now, look at what inequality I wrote. I wrote pi rho delta n, rho tensor n, pi rho delta n. This is greater than or equal to pi rho delta with some factor here, right? Exp minus n times, I'm not going to write this. This is the thing. See, and I also mentioned that these two commute. If these two, so let's call this A. Let's call this let's call this B. Okay. Now, so since pi rho tensor n equal to pi rho tensor n pi rho, you can show that AB equal to BA. In fact, right? I mean, because pi rho, it's pi rho squared itself is pi rho. So AB equal to, yeah. So you can show AB equal to BA. So it suffices to show, so in this case, since A and B are both self-adjoint and AB commute, in this case, it suffices to show that the eigenvalues of A dominate the eigenvalues of B. Now, we know this guy is essentially, if you write what this guy is, you will get this xn belonging to T delta n px, pxn of xn, I'm going to just write exn. Now, each of these terms are upper bounded and lower bounded by these exponential quantities. And hence this inequality holds.
Okay, correct. Now the eigenvalues also have the property, and because everything commutes, you can see that. Okay. Okay.
So you see again, the proof just boils down to the classical case. So
because the p's are sandwiched between the x things from the classical thing, and so you have.
Yeah, it's these probabilities happen to be the scalars for those eigenvectors, right? It happens to be the eigenvalues for those eigenvectors. So all that we are really saying is all of these eigenvalues are dominated by this exponential factor. And because they are in the typical set, it's essentially exactly what we said in the case of the classical, where we said that if you take an element in the typical set, the probability is between these two exponents, right? Exp minus n times h of px minus delta and plus delta. So it really just, if you write all these things, it really boils down to classical proofs itself.
Yeah, correct.
Convinced?
Yeah, now it makes sense.
Okay, I didn't see this message of Srinidhi.
No, sir. Now it's resolved. Like join.
Okay, fine. Yeah, Srinidhi, do you want any explanation?
Like I understand, sir.
Yeah, maybe you took a little bit of time to fix your audio, so you'll have to look back at the video a little bit. Okay?
Yeah.
Okay, cool. So I'll go to the next one. So we did what is analogous to unconditional typicality. We'll do now conditional quantum typicality, and this will come in the packing lemma. Conditional quantum typicality. By the way, all that we are doing is referred to as strong typicality. There is a slightly easier notion of weak typicality, but for all research, it's not really used much. So I'm not really bothering about it. And it's really, it's in some sense a little bit weaker. The strong gives you slightly better, handle over certain things, which, this, for you to understand, it will require a little bit more involvement, exposure to information theory. But don't worry, everything is, I mean, if you're reading the book, this is what is strong. It's not weak, because the book does both strong and weak. Okay, now the situation is the following. I don't have one operator, but I have a bunch of operators. Okay, so so recall how we did in the classical. How you did in the homework in the classical. You had one distribution Px and you studied about the typicality properties of that. Next, you considered a joint distribution Pxy, right? And here, if you look at it, if you look at Pxy, right, you can say it is Px kind of tensor Py given x. So if you look at these distributions, right? So I fix whatever is not. So look at this. I fix an x, and I look at this vector y belonging to y. So I fix an x, and I look at I look at this vector. This is a distribution on y, right? And you have a bunch for each x, right? So so if I take a Py given x of y given x tilde, I take a different one. These are different distributions, right? And you studied the notion of conditional typicality, where what you said was that if I take an xn, and so this is your x1, this is your x1 through xn, and if I generate a y according to Py given x of x1, so I generate according to this distribution. So the distribution is on y, but x1 is fixed. I figure out, I pull out a y1, then I pull out an y according to this distribution, this distribution. So I pull out a y2, and I keep doing that, and I pull the last one out according to this distribution, right? Then you showed that if my xn is typical, then this y1 and y1 through yn, this belongs to the conditional typical set. So something like this. I mean, I'm Pxy given xn with high probability, right? This is kind of what you showed. I'm going to do an analog of this. So these Py, so what you're doing?
Sir, like you said, like pulling out y1s, like, can you explain?
Yeah. So remember what you did? This was the statement you showed, right? If I take a yn such that xn yn was T2 delta n Pxy, and I look at this Py given x n of yn given xn. So you fix, you fix an xn, you fix your x1 for xn. This you showed is greater than 1 minus 2, some big thing, some exp minus n times something. Do you agree?
Yeah.
Okay. See, what are you doing by this? Okay, so let me explain, because you're not very familiar with probability. Let me just kind of explain. See, what are you doing when you do this Px of xn? What do you mean by this? What does physically this mean, right? Xn belonging to some set. Let's say some set S. So I have xn. There is some set S, right? You are pulling the first guy. Pulling means you are you take your you take your computer, you take MATLAB or something, and you choose a random number according to a distribution Px. So you'll get a number. So let's say your set X is say 1 to 10. You're pulling out a random number with some distribution Px on 1 to 10. So you pull out the first guy. Let's say you get 3. Again, you will pull out. You will get a 4, let's say. Next time you pull out, you'll get some, say 1. Next time you pull out, you'll get 7. And you do this n times, and you're going to get the last number, say 9. Okay. You're asking, what is the probability that this sequence that I ended up with today happens to fall in this set? That is this quantity, correct?
Yes.
Okay. So what am I doing? How do I say this? The other way I say it is, I pull out one guy according to the distribution Px. I pull out another guy according to the distribution Px. I pull out nth guy according to the distribution Px. I concatenate this entire vector, and I ask, okay, what is the probability that I'll fall in S? That happens to be this. And what we were able to show is that there is, in that set Xn, there is a small set P delta n, such that I will definitely fall in T delta n with very high probability. That's typicality, correct?
Yeah.
Okay. Now I'm changing the setting slightly. The first number I first fix an x1. I now have a collection of distributions. I have a collection of distributions. Y belonging to Y. Now this is a distribution. You agree? There's a distribution on Y.
Yeah.
Now I take a collection of such distributions. So I have, so I give you an example. So Y could be said 0, 1. My first distribution will be 3 by 4, 1 by 4 on on 0. So and the second distribution will be 1 by 4 and 3 by 4. So if X is 0, this is the distribution with which I'll pull Y. If X is 1, this is the distribution with which I'll pull Y. Okay. Now, so I have two distributions. What I do, I'll fix a big X sequence. Suppose I fix this sequence. Now I'll pull the first one according to this distribution. Right? I'll pull the first one according to this distribution. The second one I'll pull according to say this distribution. So I should have used the so whenever it is 0, I pull according to the so this is what it is, right? So now I get a bunch of y1 through yn, right?
Like, so if X is 0, like
yeah, if
pull
X
from
is
the
0,
distribution. Yeah.
Yeah, if X is 0, I will pull according to this distribution. I'll pull,
Yeah.
I will sample a Y according to this distribution.
Oh, like,
If
okay.
X is 1, I will sample according to this distribution. So while in the previous case, I was sampling all my Y's according to one distribution. Now I am sampling my Y according to the distribution based on the X's that I see, right?
Yes.
Yeah. So what is the probability? So suppose sorry. Okay, so suppose I consider a sequence y1 through yn. What is the probability that what is the probability that the pulled sequence will be this y1 through yn? Well, it is py given x of y1 given x1. So this is your x1, this is your x2, this is your x3, all the way into this is your xn, times py given x of y2 given x2, all the way until py given yn given xn, correct?
Yeah, yes.
This is what we denote as y given x of n of yn given xn. This is just by notation, correct?
Yes. Yeah.
Now, when I sum over some set, let's call it some set S, right? So yn belongs to some set S of py given x, n of yn given xn. What do I mean? Essentially, I have this big yn set that I could have landed up anywhere. What is the probability that if I sample according to, like, in this way, if I pull my y's according to this way, what is the probability that I will fall in a set little less, in a set capital S, correct?
Yes.
So that is what this was telling you. So there is a small set of size, an exponentially smaller set whose name is given 2t t2 delta npxy. If my xn happens to be in t delta npx, and I pull the y's according to this, this kind of a way, then the probability that I'll fall in 2 delta npxy is very large. That is the physical interpretation of the statement. Do you agree?
Yes, sir.
Okay. So that's where I'm going. So what have I done? My first y I pulled according to py given x of something given x1. The second one I pulled according to this given x2, right? All the way. And I'm telling you that the y1 to yn will land in a set t2 delta n pxy. Correct?
Yeah.
Okay. Now I will ask an analogous question. It's important that you understand this. So it's good that I elaborate. Now I'll ask an analogous question in the quantum case. See, previously I had a single px. I pulled all according to that single px. And the analog of that in the quantum was rho tensor rho, and I asked the question, where is rho? Where is rho tensor n? That's the question I asked, and the unconditional quantum typicality tells you something. Now, I will have a collection of rho x's. So I will have a collection of rho x's. So each of these rho x you should think of as similar to this distribution with x fixed. Okay, it's kind of similar to this. So now I just like I pull the y1 through yn according to x1 through xn. Now I'm going to consider rho x1 tensor rho x2 tensor rho x3 tensor all the way until rho xn. And I ask, is there a subspace in which this is localized? Do you understand?
Yes, sir.
Tejas, do you understand?
So like these rho x1s through rho xn, they are like the p of y given x1, which we had in the classical thing.
Exactly. This is analogous to the distribution with x1 fixed, the distribution on y with x1 fixed. This is analogous to the distribution of y given x2 being fixed. So now I take this particular sequence.
So then just one question. So yeah. So all these should have the same support set, right? All these rho x1, rho x2, rho x3.
Yeah, you can always enlarge them to have a one support set, right? So suppose your rho x's. So let's take, for example, just two rho 0 and rho 1. Just two density operators, rho 0 and rho 1. You can always enlarge their spaces to make them within one y, right? I mean one h.
Okay, you can just set it to be 0 for the other things which they didn't have before.
Yeah, exactly.
Okay. Okay.
Exactly. Okay. So now I ask this question. Okay, suppose I have a sequence. So just like in here, right? Remember what we did here. I'll give you an absolute exact counter statement. See here, I pulled my y's according. Sorry, I pulled my y's according to this sequence here, right? And I asked, okay, where does it live, right? That's what we did here, right? That's exactly what we did here. Now I'll take the same sequence. So I'm going to take the same sequence. I'm going to take the same sequence here, and I will say now instead of the y's, I will consider the big quantum state. So exactly these indices are coming in here. And so on. And I take this big quantum state. So the last one is rho 0 tensor rho 1. This is big quantum state. And I ask, okay, what is the dimension? Can I localize this? See, rho 0, for example, can be like exactly like previously, right? It could be 3 by 4 plus 1 by 4, 1, 1. and row 1 can be 1 by 4, but I'm going to just do, now it's not commuting, it need not commute, so I'm going to do this. Okay, so there are two states. Now I consider this thing, so I know this lives in a dimension of the ambient space has dimension 2, this has an ambient space of dimension 2. Now this big term lives in an ambient space of dimension 2 power n. But suppose I tell you something on this sequence, can I localize this guy? Can I say, what subspace it lives in? This is exactly the question we asked in the classical. Is it seeming analogous to both of you?
Yes.
So what is so in the classical thing, we had the y, the other string, which was drawn according to px1, px2. So what is this other string in the quantum case?
So you're preparing the quantum state now. So you're preparing the quantum state based on these indices. So rho 0 and rho 1 are two possible density operators.
Yeah.
And you are preparing this quantum state according to this sequence here. So it's like so what was the motivation? Remember what was the kind of the motivation? So yeah, so this question, I think your question is slightly alluding to the motivation of asking this question, possibly.
I mean, this what is the analog of this y1 through yn string in the quantum thing? That is not clear. Like the x's, I understand. Like px1 becomes rho x1 and so on. Like distribute. But
I'll tell you. See, okay, I'll tell you in some broad sense, and then I will actually elaborate on this at a later point of time. So suppose you have a transition, right? So you input x, and you get out py. So you get a y based on the based on which x you get, your y is sampled according to that distribution, right? So this is py given x of something given x, right? This the motivation for the classical thing. Do you agree?
Yeah.
Okay. Similarly, here you should think of the following. There is a device here that has a lever. Okay, that lever can be either put in position 0 or it could be put in position 1. If you put in position 0, it's going to prepare a quantum state rho 0. If you put it in position 1, you're going to get a quantum state rho 1. Now you input a sequence of digits and you get a sequence of quantum states corresponding to that sequence that you input. Okay, and you're asking, what can I say about this quantum state in some sense?
Yeah,
we will come to this exactly later. Actually, as I will describe this very setting, there will be one more question, and then we'll come to that. So for now, let's take this as a technical tool and proceed, and then we'll come to the use of conditional quantum typicality very soon. Okay, so having motivated, I'm just going to again, the proofs are very similar to the previous one, but there are some differences, and I will indicate that. So conditional quantum typicality, I will set up all the and when you kind of go through this, you have to keep that analogy in mind so that you understand what's going on. So suppose rho x belongs to is a collection of density operators. I will I'm going to enlarge their spaces to have them to be living in one ambient space. So there is an index set and there is a bunch of density operators. Our density operators are with, I would say, a spectral decomposition. I mean, what I mean is that each one has a spectral decomposition, and so let's say this, with spectral decompositions rho x equal to summation. So I should be doing something like this, right? I mean, ideally you would be doing something like this. You would say lambda j, x is fixed, but the lambda j x depends on the x. So ideally you would be writing it something like this. j equal to 1 to some d. What I will do, I know the following, right? I know lambda jx is greater than equal to 0. I know if I fix my x and I sum over my j, I'm going to get 1. So j equal to 1 to d, I'm going to get 1. So this we know. What I will do, instead of writing it like this, just to be consistent with the previous case, I'm going to write this as, so this I'm going to, in some sense call y equal to 1 to d. And we are going to say y, and I'm going to say, instead of calling this lambda jx, I'm going to say instead of p, I'm going to use q, just for something that will come very much later on. So I'll say y given x is your lambda jx. Okay, is kind of what it is. So it will be q y. I should really be just saying an index x here at the top, but how does it matter? I'm just going to say y given x, just to put it in the same framework as in the classical thing. And here I will say e. I will also say just y given x. This I could just be saying y and put an x at the top, but doesn't matter. I'll just use this notation. Doesn't matter. Y belonging to y. Okay, with spectral decomposition. So keep one thing in mind. If I fix my x, okay, so if I fix my x and I look at this ey x, inner product ey hat x. So I'm looking at two eigenvectors of the same row x. This will be delta y hat. But I can't say anything if I change my x. I cannot say anything about this. Y given x, ey hat given x hat. I have nothing to say about this. This I have no clue. Okay, so just keep that in mind. Suppose I have these density operators with spectral decomposition so and so. Okay, and let px be some distribution on x, be some PMF on x. Okay, so be some PMF on x, sorry. So what we are interested in is, we are interested in something like this: row x1, tensor row x2, tensor all the way until row xn. I'm going to define this as, for simple notation, I'm going to say this is xn. So when I say xn, this is what I mean. Okay, I'm really interested in, what can I localize this guy? And I can't localize this in general, but if my x1 through xn belongs to this t delta n px, then possibly I can say something about the dimension of this, right? This is exactly what we were doing previously. Previously, remember, we took our xn to be in t delta n px, and we said, okay, if I pull out my yn according to py given x, right, we know where yn will live, right? That's really, I'm kind of going exactly towards the direction, with now q in some sense being replacing p. Okay, but remember, they're not commuting. In the previous case, everything was commuting, and somehow everything worked out fine. So be some PMF on x. We define. So I'm going to define the conditional typical set. Remember, we define. Remember, in the classical case, we defined the conditional typical set. So now I'm going to define the conditional typical subspace. Okay. We define the conditional typical subspace. So let's say delta xn conditional. I mean, this notation can get very bad, but I'll just use something. Even the book gets very dirty, but as we go along, we kind of understand what we're talking about, and we keep simplifying it. Conditional typical subspace as, so T, there is a there should be a delta, there should be an n. Well, the n can go. and there is going to be a row xn. Span of what? Exactly what you think I would do, right? Remember, there is an EYX, right? So what did we do? Remember, what did we do in the classical? We said put all those yn such that when you stick it with the yn, you are going to fall within the 2 delta n px py given x, right? Instead of pxy, I'm writing it as, so this was what it was, right? And this was px times py given x, correct? This was our classical conditional typical set. I'm going to do exactly the same thing because my xn is fixed. I cannot do anything else. So I'm going to do E. I have also denoted it kind of in a very like a analogous way. So I'll keep that you should be able to see that screen also, and I mean that term also and this term also. So y1 given x1, remember x1 is fixed. I'll do an example so that it makes sense. Otherwise, it's very confusing, this definition. Such that when I stick the xn and the yn together, it should be jointly typical according to T delta n px qy given x. Okay, it seems weird what I'm doing, but you will soon realize, okay, it's not too much out of vogue. Okay, and I'll state this definition and do an example. Otherwise, it's very hard to understand what's going on. And the conditional typical projector, you should put the delta and the xn and all that. Conditional typical projector pi rho xn delta. I mean, this notation is crazy. Okay, everybody uses a different notation. I'm also using something different than what I myself use, but let's get the idea first. So this is just the projector on the subspace defined above. So what I'll do, I'll just do what I did previously. So yn, sum over all yn such that xn comma yn happens to fall in the jointly typical conditional set of some of these rank 1 projectors. And I will do an example so that you understand what's going on. xn okay. So that's what this is. So I'll do a good example so that okay. So I'll just leave this here for 2-3 seconds for you to kind of look at it. I think this is 14 point something. Just give me 1 second. I'll leave this on screen. I'll just tell you the index of the book. This is 15.2, particularly 15.2.3. His definition is slightly different, but if you want to kind of read this in the book, that's where it is. Section 15.2.3. Okay, let me go to the example. So let's just take 2 density operators. So I'll start with exactly what we did previously. So rho 0 is say 3 by 4, 0, 0, plus 1 by 4, 1, 1. Row 1 is say 1 by 4 plus 3 by 4 minus, just recall, plus is essentially 1 by root 2, 0 plus 1 by root 2, 1, and minus is 1 by root 2, 0, minus 1 by root 2, 1. Okay. Now, so what is my x? My x is just, x is the number of indices here. There are two indices, 0 and 1. Y is and a set of indices for the entire space in which row 0 and row 1 live. Okay, in this case, it's just two-dimensional. So I can just say y is just 0, 0, 0, 1, sorry. Okay. What is, so q 0 given 1, sorry. So what is my q? Qy given x of 0 given 0 is 3 by 4. Qy given x of, really what I'm doing is that, so I'm expanding this. So this is q y given x of 0 given 0 something plus qy given x of 1 given 0 of something, right? That's all I'm doing. So 1 given 0 is say 1 by 4. Okay, so E, what is E? 0 given 0. Well, E is 0 given 0 is 0. E 1 given 0 is 1. E 0 given 1 is plus. E 1 given 1 is minus. Q y given x of 0 given 1 is say 1 by 4. Q y given x of 1 given 1 is say 3 by 4. Okay, so now what are we doing? So I take, so let us take a distribution. Let px of 0 be say 1 by 16 and px of 1 equal to 15 by 16. Okay, so I consider a big sequence, right? So let's consider a 16 length sequence, right? Just for n equal to 16. Let's say n equal to 16. So I take a big sequence. I should have 1, 0, and all of them should be 1. So it really depends on where the 0 is. So let's just do this. This is my x16. Okay, so I think it's, yeah, the 16 terms are there. So now what do I do? It's very simple, right? So you take, so you should do, so let's say delta is say 1 by 10 or something. So what are you doing? You look at this distribution px times qy given x, right? So you're going to get something like this. So the joint distribution would be, let's say x is here and y is here. So you have 0, 1, 0, 1, right? So you have, I think you have 3 by something like this, 3 by 64, I think, and 1 by 64, I think, and you have 1 by, no, not 1, 15 by, so what do we have? 15 by 16 times 1 by 4, right? 15 by 64, and we have 3 by 4 times 15 by 16. Right, so this will be 45 by 64. This is your joint distribution. So what you're doing, you're going to, so with this xn, so you have this big xn, so we'll call this x16. So this is your x16. You are going to pull all those y16s. So y16s such that when I concatenate my x16 and my y16, the number of xy pairs should be close to your should be your t2 delta n px qy given x. So what does it mean? It simply means that you take all those y16s such that when I write my y16, so y4 is 0, the rest are all, so 1, 1, 0, 1. When I look at this, the number of ABs should be close to this matrix. That's all really that's going on. And you do EY1 given x1, tensor all the way until EYN given xn. This is your conditional typical projector. This is your conditional typical projector. So T x16, row x16 with respect to 2 delta. Delta is your 1 by, whatever I said, it's 1 by 10. So this is going to be, 1 by 10. That's all. But when you substitute, so you take, so suppose you're, so I'll do a little bit more detail. So suppose your yn happens to be, let's say, what is the high, whenever it is 1, it should be going to 0, right, with high probability. So let's say it's 0, 0, 0. Whenever it is 0, it should go to, no, whenever it is 1, it should go to 1 with high probability. So 1, 1, 1, 0, 1, 1, 1, 1, 1, 0. Let's do this way. So if this is your yn, what are you doing? You're doing E. So it will be E1 given 1, tensor E1 given 1, tensor E1 given 1, tensor E0 given 0, and so on, right? So when you, what is this vector? This is exactly what I wrote here. That's really, so it's a bunch of all rank 1 projectors that are summed together. Do you understand this?
Yes, sir.
Yeah, work this example out kind of yourself once again. So this is your typical subspace. Okay. Remember what I'm doing, I'm not including all the yn sequences, right? If I included all the yn sequences, is no big deal. I am cutting down on the number of yn sequences, right? So row 1 I know lives in a space spanned by 0 and 1. Sorry, row 0, right? Similarly, row 1 lives in a space spanned by plus and minus. Well, they are the same, but I'm just writing it this way. If I had taken all possible tensor product rank 1 operators and summed them, then I'm sure that my my row tensor n will live in this space. In other words, the projector, the trace of the projector, the overlap between the projector of that space and row tensor n will be very high. But I'm not taking everything. I'm only taking some of them because I'm restricting myself to this set. And really the question is, what is the overlap between this guy and row x16? That's really the question, right? And what is the dimension of this guy? What is the overlap between these two guys? And what can I say about the product? Is there some operator dominance, right? Exactly similar to the previous setting. Does this make sense? Or ask me and I will explain. So far, does this kind of make sense?
Yes, sir.
Yeah.
Okay, cool. what do you expect? You will get exactly what you expect. In other words, so I'm going to write these statements. I'm going to prove it in the next session. So what are you going to get? You're going to get something like this. The trace of, so if xn belongs to T delta n px, right? Then the trace of this row xn, so what is row xn? It is row x1 tensor all the way until row xn. And the conditional typical set projector carefully chosen according to this row xn delta, this is very large. You're going to get exactly the same, exp minus, I think you'll have this, 2 cardinality of x, cardinality of y. You'll get exactly the same expression. And the reason also you will see why you will get, minus something here with the 2 delta sitting somewhere here. You're going to get something like this. And you're going to get the trace. So what is the dimension of this guy? Because that's important. If this dimension is too large, there's no big deal. There's really nothing that's happening. This that is the dimension of the space, is the trace of the projector corresponding to that space. This happens to be less than exp n times. I'm going to leave this for you to guess, and I will fill this up in the next class so that it will be also similar to what you get. But let's see what your guess is. So we will do this in the session later. I will complete this, and then I will motivate the packing lemma. So maybe let me just kind of quickly motivate the packing lemma and then move. See, the idea is exactly what I said in the previous to pages. Essentially, you have this device. Okay, this device has a lever. Okay, so this device has a lever. This lever can either be put in this position, or it can be put in this position. So this is 0, this is 1. If it is put in the black position, you're going to get a particle whose characterization is rho 0. If you put it in the red position, you're going to get a particle whose characterization is rho 1. Okay. These two, unfortunately, are not distinguishable. Okay? Not necessarily distinguishable. And you have some information that you want to communicate with this quantum state. So you have some bits coming in. Okay. So you have some information bits coming in, and you want these quantum states, these prepared quantum states, to act as the information carriers. Okay, so quantum states as information carriers. Ideally, what you want to do, if you get bit 0, if you get bit 0, you will put your lever in state 0. It will prepare the quantum state rho 0, and you will give it to somebody who is going to be, who's going to somehow be able to distinguish it from rho 1 and then figure out the bit is rho 0. If you got bit 1, then you will put the machine in the lever in the position 1. It will create a subatomic particle with characterization rho 1, and you give it to somebody, and that guy will tell, okay, it is indeed rho 1. And this rho 0, rho 1, and this entire device is known to everybody. Okay, but every time you get a different bit, you want to communicate. So somehow, if the guy who sees the guy who is the the intended destination of this information, if he is able to distinguish between rho 0 and rho 1, then you have absolutely no trouble, because you put it in 0, he can tell you it is rho 0. If you put it in 1, he can tell you it is rho 1, and then you're done. So in other words, if he is able to perfectly distinguish between the two quantum states rho 0 and rho 1, then you can always use these quantum states as carrying that information bit, right? But suppose they are not distinguishable, then there is a probability of error, right? And if you recall, you know what is the probability of error? The probability of error is kind of proportional to the distance rho 0 minus rho 1. In other words, if this is large, then the trace distance between rho 0 and rho 1 is very large, then they're very much distinguishable with high probability of correct distinguishability or low probability of error. But if the distance is small, then the distinguishability is small, right? Now the question is, you want to communicate with very high reliability, say with probability 10 power minus 27. You want to communicate the bit correctly. So in other words, you want him to distinguish. How do you do this, right? So this is kind of the setting we are going towards, and this conditional typicality will kind of tell us something about how to distinguish and things like that. So actually in the next 2 classes, this whole kind of picture will become clear. But if there are any questions, I'll answer.
So I have one question.
Yeah, please.
So in the classical thing, so you first had some x, the string x, and then so let's say x1, x2 up to xn, and then you sampled the y's as per the distributions p of y given x1 and so on. So in this case, all the y's came from the same set, sort of the same support set.
Correct.
But in the quantum case, that's not the case, because these eigenvectors, they are sort of not mutually orthogonal. Like rho x1 and rho x2 could have different sets of orthonormal bases.
Yeah.
Okay, and
go ahead.
Like the analog of the y is the e's, right? The e of which you wrote, e of y given x.
No, the analog of the y's is the rho x1s.
Rho x1 is the distribution, correct?
Rho x1 is the, so in some sense, the analog of this is this, in some sense. Because the density operator usually corresponds to a distribution. So see, remember, when I prepare a quantum state with the density operator rho x1, this is not a perfect characterization of the quantum state. This is your best understanding of that quantum state.
Oh, I mean, what I thought is P of y given x, like what you have wrote, right? That distribution given x1.
This one?
No, in the first red bubble which you have.
Oh, you mean Q?
Yeah, I mean, I think so. Rho of x1 is the analog of that P of y given x.
Yes.
x1.
Yes, correct. Yes, that is. So rho x1 is analogous to this distribution, P y given x of y given x, 1, y belonging to y. Kind of analogous.
Yeah, correct.
The only thing here is, so when I take rho xj, let's say rho xj, right? This is analogous to P y given x of y given x j, y belonging to y, right? But see, here, these are all in some sense commuting. These are not commuting. Okay, so what is commuting? In other words, there is an additional element of non-commutativity that is missing in the classical sense. But so far your description is correct.
Oh yeah, correct. I mean, in the quantum it will not commute because you have this E of like what you wrote above.
Yeah.
So rho of x1 is summation something E of.
Yeah, this thing I wrote, right? This thing I wrote.
This thing. Above. Slightly above. This one.
Yeah.
So these don't commute, you are saying, for different x's, correct?
Yeah, the rho x's need not commute.
That's the difference.
Yeah, that's the difference. So it's like you're asking an analogous question in a non-commutative space.
Yeah, like what you have said, no clue there. Like that says that you cannot.
Yeah,
Okay.
correct.
Hmm.
Correct. Yeah, so we'll come to this. The picture will be slightly hazy at this point because the quantum. So there are two ways to do this. One, you do the quantum typicality, and then you go to motivate the packing lemma, and then come to conditional quantum typicality. But I was thinking I'll introduce all the tools first, and then do the and then come back and plug in the tools. So I will take this conditional quantum typicality. You will see all the statements and everything will make sense. You will wonder, okay, why are we doing this? Immediately after this, I will actually do a little bit of chapter 20. Little bit I'll motivate chapter 20, and then we'll go to the packing lemma, and all of this picture will kind of tie up, and you will see why the conditional quantum typicality is needed, what is meant by the packing lemma, what is this problem of quantum states as information carriers. So all of this will fall into place. Okay, so I have a class today at 7:30, right?
Yes, sir.
Yeah, 7:30. Cool. Both of you will be able to make it?
Yeah, I will make it.
Okay, cool. So I'll do exactly this. I will record this, post it, put the notes, and then I'll do the same thing with that lecture also.
Sir, like where are you posting the notes and videos?
I posted it in the thing, right? Did you not get it? Let me see.
Yeah, even I didn't get permission, I think so. Even I did not get that.
Really? I posted it immediately. Did it not? Okay, so
No, I mean, you asked us to write to you for the permission. So I did not email you back. So maybe if you can send me the link.
Yeah. You're right.
Yeah, I did not email you. Yeah. Okay.
Yeah, if you had not sent me that email. So by the way, I think my inbox is full and some emails are getting rejected. So I'm
Yes, I could not send you an email. Yeah.
Yeah, so I will clean up my inbox hopefully after class today. But let me, now that you asked, let me check whether I've indeed uploaded everything. So the yeah, 1621. Yeah, I have uploaded the notes and the video. It was lecture 16, right? Lecture 16. Yeah, I have indeed uploaded the video and the lecture in that link. So I can, okay, I will add both of you. I'll try myself to add both of you. Otherwise, kind of sit with me after the next class and then I will do it right then. Okay.
Okay. Sorry, I also had one question about the homework.
Yeah.
Just one quick question.
Yeah.
So this, I think it's 2.7. They talk about the fidelity of non-square operator. Sorry, this. Oh, sorry. 9.2.7.
9.2.7. 1 second. 9.2.7. So that the fidelity is invariant with respect to isometry, right?
Yeah. So when you apply the isometry, you get a non-square operator. Like
when you do euro u dagger, you will get a square operator.
Euro u dagger is a. So u goes from h to h prime.
Yeah. So euro u dagger will, is an operator from h prime to h prime, I think. Yeah, u dagger will take you from h prime to h, rho will take you from h to h, and u will again take you from h to h prime.
Okay. And both are operators. Okay, fine. Both of them are operators on h prime, correct?
H prime, yeah.
Okay, got it. Okay, thank you.
Yeah, we can meet. We can meet. Yeah, we can meet after next class a little bit longer.
Yeah, no, I think that's the only question I have.
Yeah. So like in the first question also, like I and Niranjan were able to come to a close expression, but we are not getting the exact expression.
Is it?
Yeah. Like we tried
will
the
do
same.
the sum of eigenvalues, right? You will do the sum of the roots.
Yeah. Same. We took like we wrote V as like sum of U and some and U perpendicular. Some combination of U and U perpendicular.
Just tell me where
So like we were able to get some very close expression, but we are not getting the exact expression.
No, okay. I think I have to base it on.
Huh?
Am I audible?
Yeah, you are audible, but somebody else also is audible.
Yeah.
I'm in the CS lab, so like.
Oh, okay, fine. Yeah. So let me see. I actually did this myself. I think this is, yeah, we can say it's not a big deal. I mean, it should be some algebra, but I want to see the method. I mean, it's not going to be. I hope I'm not wrong. I actually have done this myself. I did not know that it. Okay, so we'll work it out. Srinidhi, not a problem. We can work it out. I'll go through this. You tell me the steps. I'll write it down, and then we can see what's going on. I mean, you tell me the steps you've done. I'll just keep writing it, and then we can figure it out after the next. I mean, at the end of the next class, we'll just figure it out.
Yeah. Also, the first homework, the last but one question, like I still have a doubt.
Sure, we'll do that.
Yeah.
We can have a session itself, kind of a discussion session, and we can do it either today or tomorrow.
Yeah, sure.
Okay, awesome. Thank you.
Okay. Thank you.
So I'll also come for that session, which you'll have
I'll let you
about.
know. I'll send out an email to everybody. It might be it might be tomorrow only.
Yeah, tomorrow is fine.
Yeah, and I have announced the class at 7:30, right? So 7:30. Cool. Cool.